in different journals, and one is under revision. We submitted to the physical review E, and one is in preparation, which is based on the deformation of particle covered droplet in a non-uniform electric field. So today talk I divided in 5 parts. First, I will talk about the motivation or background of my research work, and then I will talk about the electric field directed assembly of the particles at droplet interface. And then I will talk about the opening and closing of particle shell at droplet interface under uniform under electric field. And I will also show you some applications. In the fourth part, I will talk about droplet deformation under a non-uniform electric field. And finally, I will talk about the electric field induced deformation, yielding and crumpling of jam particle shell. So before to go to the main slides, I want to give overview which type of the system we are using. We are using the three-phase system in which we use castor oil, silicon oil, and solid particles. Basically, we make the silicon oil droplet in castor oil, and the solid particle adsorb at the droplet interface, and we apply the electric field and study about the mechanical and rheological properties. So before to go to the three-phase system, I would like to talk a little bit about the two-phase system. Here we make the silicon oil droplet in castor oil, and we apply the electric field in vertical direction, in horizontal direction, and we saw that the droplet deform perpendicular to the direction of the electric field. Such type of the deformation we call the oblate deformation. If we change the system, if we reverse the system, we make the castor oil droplet in silicon oil, and application of the electric field, the droplet acquires the dipoles and they deform in the direction of the electric field. And such type of the deformation we call the prolate deformation. So why there is the oblate deformation and prolate deformation? Because silicon oil droplet is less conductive than castor oil, and they feel compressive electrical stress, and they deform perpendicular to the direction of the electric field, and this is in the direction of the electric field due to the higher conductivity of the castor oil than silicon oil. Here in our system, there is some flow is also happening, which is called the electrohydrodynamic flow, which I would like to show you. First, what we did, we disperse the polyethylene particle in castor oil, and we apply the electric field, and you can see that quite symmetrical ups and downs the flows with the tracer particles. So such type of the flow we call the electrohydrodynamic flows. The electrohydrodynamic flows deformation of weakly conductive droplet was first studied by the Taylor in 1966, then which has subsequently developed by the Melcher and other researchers. It was very extensively studied by the people both way by experimentally and theoretically. Now I want to move to my three-phase system. What will happen in the three-phase system? This is my two-phase system. If we add the particle at the droplet interface and we make the three-phase system, how the droplet will behave under electric field? This is the questions. Whether the droplet will behave differently than the pure silicon oil in under the electric field, or it will be deformed differently. And secondly, what will be the dynamic of the droplet, and how the conductivity of the droplet will be changes by adding the particle at droplet interface. And another question which is most important that how the electrohydrodynamic flow will be around the droplet. There was the many question which we need to know that when we add in three-phase system. First, I would like to show you that by adding some non-conductive particles at droplet interface, and let's see how they behaved. Initially, the particles were dispersed at the droplet. When we apply the electric field, they form a ribbon-like structure. Why they form a ribbon? Because as we previously slide, as I show you that there is electrohydrodynamic flow, and this flow directed the particle to the equator of the droplet, and they form a ribbon-like structure. And good thing is that the droplet behaves similar to the silicon oil, which is called the oblate deformation. But we don't know that what is the magnitude of the droplet deformation, whether there is some difference in the magnitude of the droplet deformation, which we will discuss in the next few slides. What happens if we add the conductive particle at drop interface? How the droplet will deform? So when we add some conductive particle at drop interface and we apply the electric field, what we found that particles form a change from pole to pole, and the droplet deform in the direction of the electric field, which is called the prolet deformation. So there is some research group, they are already studied about the two-phase system. When I joined as a PhD student in our group, there was some literature was already available about the deformation of the droplet under two-phase, three-phase system, but it was not extensively studied as the two-phase system. So when I joined, my task was that to study how the particle in three-phase system, how the particle concentration changes the magnitude of the droplet deformation, and how the electrohydrodynamic flow is affected by changing the particle coverage at the droplet interface. And another task was that to see how the particle arrange, if we use the different conductivity of the particle, how they can arrange itself at droplet interface. And in another task, we plan to do some more experiment, which by attaching the droplet to the one of the ITO coated electrode and see how the droplet deform under the application of the electric field during the compression and decompression of the droplet with the help of the electric field. And another task is that to study mechanical properties of the non-spherical particle shell, how these type of the shell is behaved under the electric field, and how they changes the shape. As I said that there is some group which is already working on the three-phase system. Here I want to present some of example. There is one group which is Orime et al. The group is from Lahoska from the Northwestern University. They studied about the particle structuring at droplet interface. They concluded that the particle structuring at droplet interface in an electric field depends upon the polarizability of the particles and concentration of the particles, and as well as the applied electric field. So they arrange itself in different way with depends upon the properties of the particles. Now there is another group who studied about the colloidal cages. They make the two different type of the colloidal cages. One is the fluid-like colloidal cages, another is crystalline-like colloidal cages. What is the difference in fluid-like and colloidal cages? In crystalline colloidal cages. In fluid-like colloidal cages, they use the small concentration of the particle, and the particle was not well packed, and they behave like a fluid-like colloidal cages. When they use higher concentration of the particle, it behaves like they behave like a crystalline structure. There is one more example for they studied about the curvature distribution, which depends upon the changes of the shape of the droplet, and also the curvature depends upon the particle packing. So they studied how the curvature changes when the droplet is changing its shape. There is one more example I would like to present here, which is about the deformation of the elastic capsule under electric field. Here the researcher studied about how the droplet elastic capsule deform under application of the electric field, and also they showed that the formation of the wrinkling at droplet interface. This is the overview what the people has worked on the three-phase system and for two-phase system. Now I want to move to my experimental setups. Here this is my experimental setup, which we use to digital camera. One is to see perpendicular to the direction of the field. One is to study the droplet in parallel to the direction of the electric field. This is our sample cell, and we use XY stage to align our droplet with the digital microscope. And here we used voltage amplifier, which amplify the voltage around 1000 volt, and this is the signal generator. This is our sample cell. We make the droplet. in castor oil, we apply the electric field in the direction in horizontal direction. Now I want to talk about the system of interest, how we make the droplet, how we make the three-phase system. So here we make the Pickering. Here we make the droplet, which is covered by the polyethylene particle. Initially, what we do, we disperse the solid particle in silicon oil droplet, and we make the such dispersion in castor oil by using the micropipette. Here is the micropipette. We make the droplet, and initially all the particles were inside the droplet. When we apply the electric field, the particle started coming, reaching to the droplet interface, and after a few minutes they form a fully covered droplet, and we also called it the Pickering droplet. The binding energy of the particle at drop interface, which is depends upon the square of the diameter of the droplet, surface tension, and the contact angle. In case of the microparticles at the droplet interface, the binding energy is approximately 10 to the power 4 kBt. It means that it is quite high. The particle cannot detach from the droplet interface easily by touching the droplet through the micropipette or by under the application of the electric field. Here I want to show you the schematic diagram. This is the particle with have the three-phase contact angle. Number one is particle castor oil, silicon castor oil, and particle silicon oil. Now I want to talk about how the droplet deform perpendicular to the direction of the electric field when we apply the when the droplet is subjected to the electric field. Here we took a silicon oil droplet in castor oil, and we apply the electric field. As I said that the silicon oil droplet is less conductive than castor oil. The charges build up from the outside from the castor oil at the droplet interface, and they have the compressive electrical stress, and the droplet deform perpendicular to the direction of the electric field. And they have the two type of the component of the stress component. One is the normal component, which is balanced by the surface tension. Another is tangential stress, which is induces the electrohydrodynamic flows. Now, if we add the particle at the drop interface, what will happen? When it is covered by the fully covered droplet, when it's covered by the particles, this tangential stress will be absorbed by the particles, and no induced electrohydrodynamic flow will be around the droplet, as we saw in the previously with pure silicon oil droplet. I will show you in more details how the such flow is changes with the particle coverage, and I will talk in the more detail in the next few slides. Now, question is how we calculate the magnitude of the droplet deformation. Here we use the Taylor model droplet deformation. He has given the equation where we measure the minor axis which is along the direction of the electric field, and this is the major axis which is perpendicular to the direction of the electric field. And if we use this formula and put the value of these length, and we calculate the magnitude of the droplet deformation at any instant. So what we found, if this deformation is negative, we call that oblate deformation. If the deformation is positive, such type of the deformation we call that the prolate deformation. And what parameter the such deformation is dependent on what parameter? The question is that. So answer is that the deformation of magnitude is depends upon the radius of the droplet and permittivity of the exterior fluid, which is castor oil, and applied electric field. And also it depends upon the surface tension. SR and lambda is this the dimensionless ratio, where it is defined as R is defined as the conductivity of the interior and exterior liquid, which is interior means that silicon oil droplet and exterior means castor oil. And S is the permittivity ratio, and lambda is defined as the viscosity ratio. So this was the my research background and what was my motivation. Now I want to move to my second part of my talk, which is based on the electric field directed assembly and organization of particles at droplet surfaces. How the electric field can be assigned the assemble the particles at droplet interface, which is where we use different type of the concentration of the particles, as well as we changes the particle conductivity. So here we use polystyrene particle with different particle concentration. We plotted the deformation magnitude against the particle coverage, and the droplet is subjected to the 170 volt per millimeter for all the experiment. What we found that? We found that we started from pure silicon oil droplet, and we increases the concentration. We use around 12 different concentration of the particle covered droplet, and we found that the magnitude of the deformation of the droplet was increases in the negative direction because the droplet deformed in oblate shape. So here we use only, here I showed only just 4 particle concentration. Why the question is why by increasing of the particle coverage the deformation magnitude is increases. Polystyrene particle is less conductive than silicon oil droplet, and when we add the particle at drop interface, the conductivity of the droplet is decreases. First thing is happen with changes of the conductivity of the droplet. Second is that as we talked in previously, there is no electrohydrodynamic flows when the droplet is fully covered. It means that when it is not fully covered, there is a electrohydrodynamic flows around the droplet, and due to which there is some charge convection. It means that they convect the charges through the due to the electrohydrodynamic flows. If they convect the charges, there is a less number of the charges is built up at droplet interface, and they exert the less electrical stress. But when there is no no electrohydrodynamic flows, no charge convection, and due to which droplet feels higher electrical stress and they deform the stronger. These two main reasons due to which the droplet deformation magnitude is stronger by increasing of the particle concentration or particle coverage, you can say. Now we change the conductivity of the polystyrene particles. We use the polystyrene 16. 16 means that polystyrene particle is sulfonated for 16 minutes. What we found that? We found that when the particle concentration was around 0.3, the droplet was in oblate deformation, but when we increases above 0.3, the droplet went from the oblate to prolate deformation. Why this has happened? Because when we increases the particle concentration, the particle form the chains from pole to pole, and they stretch in the direction of the electric field, and it is increases with the increase of the particle concentration. Now we used another more conductive particles. What we found that with very small concentration of the particle were in oblate deformation, but when we increase little bit higher, you can say 0.15, the droplet started going to the prolate deformation. But we cannot, in this very high conductive particles, we cannot use the very high concentration of the particle because the droplet is stretched quite strongly and they get breaks. So it means that here the dipolar interaction which is increasing by increasing of the particle conductivity. So what parameter depends upon the particle dipolar in particle interaction, which is the dipolar interaction between the particles. So here we use the formula which depends upon dipolar forces depends upon the exterior fluid of the liquid and electric field strength and particle radius and the particle separation. There is one more parameter which is beta, and beta is defined as the conductivity of the particles and conductivity of the fluid. Here I will present two examples where beta is 0.1. We use the polystyrene particles and we calculated the beta, which is 0.1. When we apply the electric field, it forms a ribbon-like structure. So there is no dipolar interaction. There is another example where we make where we calculated the beta, which is around 1. Under the application of the electric field, they form a dipolar chains and they from pole to pole, and it means that dipolar interaction, which is mainly defined on the beta parameter, because in our previous slide we put all the parameter like exterior fluid, electric field, and particle radius, and everything was the same, just we changes the beta. So beta is a parameter which can play a role to formation of the chains at the droplet interface. Now here we use the changes the beta. Now how we can arrange the different particle conductivity at droplet interface, where I will show you the competition between the dipolar interaction and the electrohydrodynamic flows. So here we use different type of the conductivity of the particles. Here we sulfonated polystyrene particle for 4 minutes, 8 minutes, and 32 minutes. If you will see that the dielectric constant is increases with increasing of the sulfonation timing, and also the electrical conductivity is increases. What happened with the 4 minute? When we apply for the 4 minute, we found that the droplet form a ribbon-like structure because electrohydrodynamic flow is dominating. But when we apply the electric field for the 8 minute of the sulfonation of the polystyrene particle, they form chains at the middle of the droplet, which is called the equator of the droplet, and also they forms chains. It means that dipolar interaction as well as the electrohydrodynamic flows both are acting together. But when very high conductive particles, when we used 32 minutes of sulfonation, they form the chain from one pole to one other pole. It means that they form the dipolar interaction was dominating over electrohydrodynamic flow. Here from this result we can see that the particle can structures at droplet interface by changing of the particle conductivity, electrical conductivity of the particles. Now, if we don't want to change the electrical property, what is other parameter due to which we can change the particle structuring? So there is another parameter, which is the frequency. If we will play the frequency, we can also structure the particle. So here we use the conductive particle. This is the perpendicular view, and this is the parallel view to the direction of the electric field. We just changed the frequency of the electric field. When we apply the 0 Hertz, there is no particle at the pole. But when we apply the 200 Hertz, what we can see that the particle covers the whole droplet and they form chains from one pole to another pole. So it means that electric field is also a parameter where we can structure the particle by changing the frequency of the electric field. Now I want to move to the next slide, where as I said in my previous slides that I will show you about the electrohydrodynamic flow, which is affected by the particle coverage. Here we use the different particle coverage, which is a pure silicon oil droplet. We found that the flows around the droplet was quite strong, but when we started increasing of the particle coverage, we found that the electrohydrodynamic flow started decreasing. When the droplet was fully covered, there was no flow was found around the droplet. As I said that when fully covered droplet, there is no tangential force, and this tangential force is absorbed by the particle, and there is no induced electrohydrodynamic flow. What is another parameter? How we can control the electrohydrodynamic flow rather than by changing the particle concentration? This is by changing the particle properties. If there is a conductive particle, we can also control the electrohydrodynamic flow in our system. Here you can say they form the chains from one side to another side. There is no flow because the particle conduct the charges through the chains. But here you can say there is no chains. It means that there is a charge is built up at interface and there induces the electrohydrodynamic flow due to the tangential force. But there is the flow is really smaller as compared to the pure silicon oil. But here you can see that it is covered the whole droplet from one pole to another pole, and they conduct the charges, and we found that the no flows. So it means that we can manipulate the electrohydrodynamic flows by changing the particle concentration, and also by changing, if we don't want to use high concentration of the particle, so we need to use some conductive particle just to make the short circuit, like to just make the short from one pole to another pole to conduct the charges. So also we can control the flows in the system. Now I want to move to my next part of the slides, which is based on the opening and closing of the particle shell under electric field, and I will also show you some of its applications. So before we start my work, I want to show you some motivation where the people has already been work on the manipulation, opening and closing of the particle shell on the droplet interface. They use magnetic liquid marbles. What they did, they open and close the particle shell by using the magnetic field. In the presence of the magnetic field, the liquid marble get open from the top of the droplet. When they remove the magnetic field, that particles cover the whole droplet. So there is another techniques the people use to open and close of the particle shell, which is ultrasound. Here they use the ultrasound source, and this is the liquid marbles. They bring the source near to the liquid marble. They open the particles shell from the top of the liquid marble. When they remove the ultrasound, the particle covers the whole droplet. It means that such system is completely reversible system. And they also propose the application, which is can be used as the microreactor. What they did, they create the cavity by using the ultrasound, and after the creation of the cavity, they put the KMNO4 inside the droplet and they just close it. So they can use as a microreactor. Now I want to move to my system. This because the idea comes from here. We have the electric field, which can deform the droplet, and we have the electrohydrodynamic flow in our system, which can convect the particles. So we can also get the opening and closing. This is our hypothesis. So now here I want to show you the video. This is the perpendicular view. This is the parallel view of the same droplet. First, what we did, we attach our droplet to the one of the ITO coated electrode through the plastic ring. We attach our droplet in such a way that there is no particle are inside, and we apply the electric field. What we can see, up to the 125 volt, there is no opening area was observed, but above that we can see that the opening area is created. Why this is happening above 125 volt? Because below at 125 volt, our droplet was quite jammed and it behaves like a solid droplet, and there is no flows was induces. But when it deformed enough, the electrohydrodynamic, the particle get enough place to move on the droplet, and the electrohydrodynamic induces and it pushes the droplet, and we found that the opening area. We also calculated the magnitude of the deformation from the right panel of the video, and we plotted the deformation against the electric field. What we found that the when electric field was increases, the deformation was increases, but when we started to the decreasing of the electric field, our system exhibited the hysteresis. We also calculated with this magnitude of the opening of the particle shell against the electric field, and we also similar to the droplet deformation, the opening area is also exhibited the hysteresis. Why such hysteresis is happening in our system? So we studied a little bit in more deeper, and we changes the particle concentration, which we changes the particle concentration from 0 means that silicon oil, and 1 means the fully covered droplet. We plotted the deformation against the applied electric field. What we found that when under the compression and decompression of the pure silicon oil under electric field, we found that the deformation was retraceable. But when we added the particle, droplet started exhibiting the hysteresis. And we found that when the droplet was fully covered, it exhibited the very strong hysteresis area. And then we plotted the hysteresis area versus particle coverage. We found that at the lower particle concentration, the hysteresis area was not influenced quite a lot. You can say around 0.6, but above the 0.6 of the particle concentration or particle coverage, you can see that it is sharply increased. Why this is happening? What we found that the, in our system there is a heat dissipation. From where this heat dissipation is coming from? So this heat dissipation is coming from due to the rotation of the particles. There is our particle are rotated at the droplet interface, and also there is some gliding of the particles, and there is some viscous drag forces. These forces are increasing with the increase of the particle concentration, which dissipated the higher heat dissipation and increases the hysteresis area. Due to the heat dissipation, when we started decreasing of the electric field, we required the small energy, or you can say the small force, to deform the droplet, and we found the hysteresis. Now I want to move the some application which is based on the optical diaphragm. How we can use as a optical diaphragm the such type of the opening and closing of the particle shell. Here we use our laser source, and here we use the intensity meter on the other side of the cuvette, and we apply the electric field. What we found under the application of the electric field, the opening area is created, and the light is started passing through the droplet, and we measure the intensity. When we turn off the electric field, the area, the droplet is covered, the whole particle covers the whole droplet, and it is block the laser light. This is a completely reversible process we use for the many cycles. We found the similar result. Now we also calculated the intensity of the light against the electric field. What we found that the intensity was zero, around 80 volt per millimeter of electric field. This is because there is no opening area is happening, but above that the opening area is created, and the intensity of the light is increases. But when we start decreasing of the electric field, we found that the hysteresis is similar to the opening and closing of the hysteresis, which is exhibited in opening and closing of the particle shell. Now there is another application which is based on the inspect of interior content of particle covered droplet and manipulation of the droplet liquid. How we can inspect the interior content of the particle covered droplet? Here we use the circular electrode. We apply the constant electric potential, and we bring near to the droplet. We created the opening area, and if we have the camera inside this circular electrode, we can see what is inside the particle covered droplet, which type of the material it is. And if there is we want to see some reaction time and etc., we can see through the camera. But so far they are not implemented, but we are expecting that in future the people can use it. There is another application which is manipulation of the particle. Here we can extract the liquid from the droplet, and we make the jam particle shell. There is another application which we can add the particle suspension, and we can make the patchy shells. So this is the some application about the opening and closing of the particle shell. Now I want to move to my next part of talk, which is droplet deformation on the non-uniform electric field. So this research project, the idea of this research project comes from here. By seeing that the deformation of the droplet in non-uniform electric field, we go through some literature survey. We didn't find so much work on the deformation of the particle covered droplet in non-uniform electric field. Then we started studying in more deeply. So here we use the different size of the top electrode, which is from the flat electrode to the pin electrode, and we plotted the deformation against the electric potential. We found that the droplet magnitude was strongest with the flat electrode, but when we decreases the size of the electrode, we found that the droplet was least deformed with pin electrode. Why it is happened? As we know that in uniform electric field, the electric strength is almost similar, same intensity in the system. But when we go to the non-uniform electric field, the electric field strength is decreases with the distance of the electrode. When we apply the very small electrode, the strength of the electric field is drastically changes, and it is very small. As a result, there is a small number of the particles build up at interface, and they have the smallest electrical stress. This is now we also did some more experiment. I'm not presenting here. We saw that the electric field intensity is increases with decreases of the diameter of the droplet. So we plan, why not we do some more experiment by decreasing of the distance between the top and bottom electrode, and let's see what is the effect of the non-uniform and uniform electric field on the droplet deformation. So we did some more experiment where we changes the distance between the top and bottom electrode. We started from the 12 millimeter of the initial distance between the top and bottom electrode, and we decreases. What we found that with the circular electrode with the diameter is 0.7 millimeter, we saw that the deformation was smaller in magnitude is compared to the flat electrode. But when it touches the droplet, we found that the magnitude was crossed with the magnitude of the droplet deformation with the circular electrode cross the flat electrode. Why it is happened? Because as I said that at the tip of the electrode in the non-uniform electric field, the electric field is concentrated. When it touches the droplet, more number of the charges is transferred to the droplet, and the droplet feels higher electrical stress and deform sharply. To validate our data, we also did some theoretical calculation. We found that this quite consistent our result, and our theoretical calculation is agreed with our experimental result, and it validated. So here is also we use the circular electrode and flat electrode, and we found this is crossing. This is the qualitatively it support our experimental results. Now I want to move to my last part of my talk, which is based on electric field induced deformation and yielding and crumpling of the jam particle shells. Here we use the jam particle shell, which is initially in prolate shape, and we subjected to the electric field. Here we plotted the electric field versus time and the deformation versus time. What we found that from 100 volts to up to the 225 volt, there is no changes in the shape of the prolate deformation, but above this there is some changes due to the rearrangement of the particles. But when we apply around 272 volts, we found that the particle changes, droplet changes its shape from prolate shapes to the oblate shape. Why this is happening? Why not they are changing the shape at the lower electric potential? Because elastic energy of the particle shell at the lower electrical state is stronger than the applied electrical state, and the droplet is remain in prolate shape. But when we apply the strongest electric field, which is around 272 volt per millimeter, what we found that the applied electrical stress overcome the mechanical resistance of the particle shell, and they deform the droplet from prolate to oblate shape. The result determines that such type of the particle shell behaves as a Bingham plastic material. At lower electrical state, they behave like a solid material, but when we apply the stronger electric field, it behave like a liquid material. After seeing after studying the such type of the shape, we plan to study a little bit more deeper. Why not we can change the curvature of the such type of the droplet and see that how the mechanical properties of the shell is changes. So here we prepared the 5 different shape of the droplet, and we plotted deformation under electric field. What we found that most elongated droplet it deform at a higher electric field, whereas the least aspherical droplet is deformed at lower electric field. And here the volume of the droplet we put the remain same, just we changes the shape of the droplet. And instead plot, we can see that the data is collapsed. Here we calculated the curvature. The curvature was calculated by at electric pole, and we divided the electric field with the under root of square root of the curvature. We found that the deformation data was collapsed. But here you can see the blue line with up triangle. It is not collapsing. Why it is not collapsing? Because when we apply the higher electric field, the droplet undergo to the electrorotation. We have another part of our study. I am not including this paper in our talk, where we showed that the droplet, when we apply the above the critical electric field, the droplet undergo the Quincke rotation or electrorotation, and we need higher electric potential to collapse the particle shell from prolate to oblate shape. So here we changes the two parameter. Number one, which is aspect ratio, another is curvature. So we were to have to rule out the one of the things. So here we did some additional experiment where we make the aspect ratio is constant, but we make the different size of the droplet. What we found that the most elongated droplet, or you can say the biggest droplet, collapse at lower electric field, whereas the smallest droplet collapse at a stronger electric field. Similar, we calculated the curvature at the pole and we divided with the electric field, and we found that the data is collapsed. This result proved that the curvature is really affecting on the mechanical properties of the particle shell, and we found that the EY, which is the critical electric field, where the droplet is went from prolate to oblate to prolate deformation, which is directly proportional to the curvature of the droplet. After seeing the mechanical properties by changing the curvature, we study a little bit more in deeper. We plan to see why not see the effect of the particle size on the mechanical properties of the particle shell. Here we prepared the different size of the particle shell, which is from 2 micrometer to 100 micrometer particle covered droplet in prolate shape of the particle covered droplet. We subjected under the electric field. What we found, the biggest particle is changes its shape from prolate to oblate at strongest electric field, whereas the smallest particle is changes its shape at lower electric field. The result shows that the mechanical properties is increasing with the increasing of the size of the particles. But why? Question is why it is changing. We analyze our data a little bit in more deeper. We saw that smaller particle, they have the motion in plane. Here you can see that there is a particle motion in plane, whereas when we use bigger particle, we saw that the very small particle were in plane, and the most of the particle motion was out of the plane. When we apply the above the 200 volt, we saw that the bigger particle, there is some ridges as I showed you here. These ridges stress the applied electrical stress in the form of out of plane movement of the particles. Therefore, they can accommodate the stronger electric field, and but due to the in-plane motion of the particle, they cannot accommodate the stronger electric field, and they change its shape at lower applied electrical field and release the stress by changing its shape from prolate to oblate shape. This is the reason why mechanical properties in our system is changes by the changing of the particle size. Now I want to move to I would like to show you how the absorption of the particle shell under the different applied electrical field. Here we use here we subjected the droplet in different electric field from 350 to 1050 volt, and under the application of the electric field, the droplet changes its shape. When we apply the weak electric field, we found that there is no formation of the wrinkling at its interface. But when we apply the 1050 volt, we found that the particles forms chains at droplet interface. Such type of why at a strongest electric field the particle forms wrinkling. This is the reason, because when we apply the weakest electric field, the particle get enough time to rearrange at the interface, and they release the stress by changing of the shape from prolate to oblate shape. But when we apply the strongest electric field, the particle did not get enough time to rearrange itself, and they release the stress by formation of the wrinkling, and they change the shape from prolate to oblate. Now we also calculated the curvature distribution during the phase changes and the effect of the electric field on the curvature of the droplet. Here we draw the contour on the two-dimensional droplet, and the droplet is subjected 350 to 1050 volt per millimeter. When the electric field was 0, the curvature was maximum at the principal axis. But when under the application of the electric field, when we apply the weakest electric field, we can see that in the middle of the figure, this is like rhombus-like structure, and the curvature was maxima and the both principal axis. And at the ordinal direction, it was quite flat. But if we will compare with the 1050 volt, this is when we draw the contour, it looks like the circle, and the curvature was distributed uniformly. Here we plot the such type of the curvature distribution on the polar plot. In the polar plot, we can see that here in the all polar axis, the curvature was maximum when the droplet was subjected to the lower electric potential or electric field. Sorry, when we apply to the stronger electric field, they are almost like circle. Now question is that I showed you that the formation of the wrinkling and how this wrinkling affect when we changes the particle size. Here we use the different particle size from 2 micrometer to 100 micrometer. Here we showed only up to the 50 micrometer in the figure, and we calculated the wavelength between the two wrinkles, and we plotted against the particle diameter. What we found that the wavelength increases with increasing of the diameter of the particles, and it is wavelength of the particle is directly proportional to the square root of the diameter of the particle size. This is quite universal relationship, because other researcher has studied about formation of the wrinkling with different particle size on the liquid-liquid interface and the liquid air interface, and they estimated the same relationship as we found it here. Now here I would like to conclude my talk, and I will summarize it. First, what I showed you that the surface particle and its coverage affects the electrical and deformation of the properties of the droplet. When we use the non-conductive particles with the different particle concentration, the droplet was remain in the oblate deformation. But when we changes the conductivity with the different particle concentration, the droplet went from the prolate to oblate deformation. Now, I also show you that how electrohydrodynamic flows and dipolar-dipolar interaction can be used adaptable method for structuring the particle at droplet interface by using the different frequency of the electric field. And also I showed you that the application opening and closing of the particle shell can be used some applications. I also showed that how the electrode geometry can be affect the magnitude of the droplet deformation, and I presented data about how the droplet of the curvature affects the mechanical properties of the non-spherical Pickering droplet, and I showed you that how the curvature is distributed at the droplet interface and how the curvature is affected by the application of the different electric field. And finally, I showed you that how the electric wavelength is formed at the droplet interface and how it get affected with the diameter of the droplet. Now, that's it from my today's presentation. And but I would like to show you my attended conference. So far, I attended the 10 conference in international and national conferences where I presented my work in poster presentation and oral presentation. And so far, I attended the 3 scientific visits. One is Harvard and one is Slovakia Academy of Science in Košice, and another is Department of Physics, University of Oslo. And I have the publication with all three collaborators. Finally, I would like to say thanks to Professor Tomasz Harnowski and Professor Bigny Rozinek and Professor Arek Yusufczak. And I would like to say thanks to Dr. Alexander Mikkelsen. And I also say thanks to the National Science Center for the funding through the Preludium and Opus program. Thank you for your attention.